My name is Alanda Kriener, and this is my Physics 2 Lab 4, where we will be observing Faraday's law and a magnet falling through an aluminum foil tube. The purpose of this lab is to apply Faraday's law in observing the behavior of a falling magnet through a tube of aluminum foil and creating a computational model to compare with our observed results. Important physics concepts include the magnetic field of a bar magnet, which we can derive via the Biot-Savart law, the relationship between time-varying magnetic field and the induced Curry electric field using Faraday and Lenz's laws. Newton's second and third laws, along with superposition, will be important when calculating the forces on the bar magnet, and here is a preview of our computational versus experimental results. Following the experimental instructions, I positioned the bar magnet above the foil tube with the north side facing down so that the magnetic dipole moment points downwards since the loop is on axis. We don't use a Ferris tube here as it would affect the magnet's behavior. I then dropped the magnet through the tube of foil and measured the time it took to fall through the tube, repeating it 5 times to find the average time. Since we are interested in finding the force from the induced magnetic field of the loop from the external field of the bar magnet, our system here is the bar magnet, and the tube and everything else are surroundings. Other initial conditions include the geometry of the foil tube, the magnet's mass, and the magnetic dipole moment of the bar magnet, which I calculated earlier in Lab 2. Here are my experimental results. You can see there are 5 trials and 5 recorded times of the magnet falling through the tube. And here I observed that the magnet seems to sort of float through the tube by falling slower than I would expect when dropping it just in free space, and the only force acting on it being gravity. This observation suggests that the tube is exerting an upward force on the falling magnet. To computationally model this experiment, I used the starter code, which includes the objects of the magnet in the tube, as well as the initial velocity and position values. I then included my initial conditions as stated earlier, and then created a function for calculating the magnetic field due to the bar magnet using an equation derived from the Biot-Savart law. Next, I created a function for calculating the rate of change in magnetic flux through each ring in the tube, which I used from the equation shown previously. I used Faraday's law to then calculate the induced current in the ring due to the magnet, and calculated the force exerted on each ring by the magnet, which should be equal and opposite to the force on the magnet due to the tube because of Newton's third law. Lastly, I calculated the net force acting on the magnet, including the gravitational force, and used Newton's second law to update the position and velocity of the magnet in each iteration. Here is the output from the computational model, and as you can see, it predicted a fall time of 0.855 seconds, which is about 0.4 seconds less than my observed time. The red represents the north end of the magnet and the blue the south, so it falls north end facing down as we did in the experiment. Because the velocity is negative throughout the bar's time in the tube, the velocity time graph confirms that the net force in the magnet is in the negative y direction. This tells us that the magnitude of the magnetic force of the tube on the magnet is less than that of the force of gravity. Some sources of error here is that my foil was pretty thin, which, could have impacted the interaction between the magnet and the foil, and there was definitely some imprecise time observations. There could have been surrounding interactions and inconsistencies among the alignment of the magnet with the tube. To further understand our model, we can answering the following questions. So to start, which color represents the clockwise and counterclockwise directions respectively? Well, the blue represents the clockwise current and the red represents the counterclockwise current. If we have this orientation, then the motion is actually slowing the magnet down, which is what we want to see since this matches our observations. If we flip the magnet around, nothing much changes as the magnet still falls slower than it would due to gravity alone, but the induced current here would flow in the opposite direction, clockwise, due to the flipped magnetic moment direction. The observed and modeled time here are relatively close, they're about 0.4 seconds off, but the computational model could be more accurate by using smaller time steps in the iterations, and we could have compensated for air resistance. And in the velocity versus time plot, we see that when the magnet first enters and exits the tube, the forces are unbalanced, but while the magnet is in the tube, the forces of gravity and magnetic force are relatively balanced. We can see this because the velocity is not changing. Now let's answer some what-if questions. So if the resistivity of the conductor was reduced as close as possible to 0, how would the dynamics change? Well, Ohm's law suggests that the current in the tube would be very large as I is equal to EMF over R, and R is in the denominator, which would increase the time for the magnet to fall through the tube and increase the force of the tube on the magnet. On the other hand, if holes or slits were cut into the tube, the model would include less full rings, making the magnetic force due to the tube decrease, decreasing the overall time it takes for the magnet to fall through the tube.